Our next session is about PNNL and WSU research highlights, so panelists please sit in from here. And our first speaker will be our PNNL colleague, Jacob Wright. Jacob Wright is an advisor on the grid communication and architecture engineering team at PNNL. He is the director of the grid CRED. So to save some time, just ignore the bio.
Okay. Thank you. So you got the introduction. I have good news. I have bad news. The good news is that we're over halfway to the break. The bad news is that the break's going to start late. But I'll try and do what I can to make up the difference here. Slide advance must be here. So I have three pretty modest goals for this presentation. The first of which is I want to build off of my presentation last year. So last year I was sitting in this same kind of information-saturated afternoon session, eagerly anticipating what really the meat of the conference is, which is the roundtable that we'll cap with, because then that's when we get all the great ideas from industry. But in that course of that presentation, I gave an introduction to what grid CRED is. And so my goal for this year is just to build off of that and to give a status update on what's transpired in the past year. Second goal is to provide some important context for what I really think that this presentation is intended for. It's a feeder to the poster session. So please, please, please go to the poster session. You're going to get a chance to talk to other very valuable members of the grid CRED team. Trevor Hardy sitting in the second row, Kit Parker as well. We have a great big 3-foot by 4-foot poster where we're going to get into some serious detail. And so this will just give you some context so that you'll be able to confidently approach that poster. And then the third thing that I want to do is just kind of bolster some of the relationships that have been built with the AGI advisory team. So this roundtable that's to follow. Many of these members have gotten one-on-one introductions and conversations on this topic. And so hopefully that'll become kind of abundantly clear as we dig into what exactly this is. So grid CRED, if you may remember from last year, it's a platform that's intended to bolster regional analytics. We've talked a lot about what needs to happen at the Pacific Northwest level so far today. Grid CRED is the capability, the computing platform, and the research body to make sure that that activity can take place in a timely, effective manner. One of the things that I think is timely in terms of helping drive the need for what this Center for Reliable Electricity Delivery can do is coming out of the call to action from the July 7th DOE report, of which there was some significant PNNL contribution. Don't know if you're familiar with that, but it talked about the fact that there was resource adequacy analysis in that report that could have benefited from greater in-depth engineering assessments at the regional or utility level. And that the call to action from the second to last paragraph of that executive summary is that we would see strengthened regional engagement, strengthened collaboration, and a robust data exchange. And so that really does serve as the foundation for what we're trying to do in this platform. We are trying to convene the right experts at the lab level to partner with regional entities, regional utility experts, to partner in their data to help build out the right tool sets and the right model to do the complex power systems analysis that would lead to more robust outcomes and more robust decision making. That was kind of highlighted by that regional adequacy report of last month. And so the thing that has happened so far to date is we've really basically been building out the use cases for the work that the platform will support. We've been doing quite a bit of regional engagement. Jess Kincaid, another PNNLer, who was instrumental in helping me set up a number of different discussions across the region to increase engagement, awareness, and excitement in the platform's capabilities. You also saw some synergy with just what like Anamika and Wei were talking about from the AGI perspective. Many of the research thrusts that they were talking about are complementary to the use cases that are being developed for the GridCred platform. And then what we have, let's see, this fourth slide is the material work that is really taking place over the last year is related to one of the funding sources, the Department of Commerce with Washington State, a significant outlay for computing infrastructure. So we actually have compute hardware, CPU, GPU, storage, architecture. There's contractual bounds, but I'm kind of holding to the fact that what we see here also is not just this computing capability, but we want to store the data, but have it available for collaboration. And again, so that's really what the crux of it is intended to be for. So that is essentially the truncated, highly truncated, efficient presentation of this material. And again, I think the objective really is to get you into the poster session. So I'll give some time back, I think, at this point. And who wants to give an introduction for the second speaker?
Thank you very much, Jack, for saving the time. And also, as Jack mentioned, please do come to the wine reception and to talk to the poster presenters. So our next speaker is Mani, so I already introduced you. Everyone knows you.
Thank you, Wei. I thought you were going to try my last name.
Oh, Vankanta Subramanian.
Oh, okay.
I practiced several times.
Well, that's a quiz question in every final I give. Ask them to write my last name. Okay, today I'm here to talk about an exciting new project that we have that is led by Stanford University. Both PNNL and WSU are sub-recipients of that project. So this project is about resilience, and it is a multi-university consortium that has been formed under DOE funding, and it includes I think 12 or 13 universities. It has NREL, NRECA, and also a couple of universities in Canada and one in Mexico. And the theme is to think about resilience in a rigorous, detailed approach, and to develop some new methods. For instance, how do we measure resilience, or what should be some requirements on resilience. And so it's a very broad theme project, and the project lead is Professor Yinesh at Stanford. Somehow the last name is, her last name is not Stanford. Comma missing. So it's Avenado, anyway. And it's a 3-year project. It's a $20 million grant, which is then distributed to several universities, and we are fortunate to be part of this team. And in our case at WSU, we have myself, I am the lead for the WSU portion of the project. Anamika and Anjan couldn't be here, and Noel and Piyush is a postdoc, and several students. Marshall is here, I saw, yes, and Yash is here, and also Rupesh I saw this morning, yes, and Shishi and Saugat. So we have a fairly large team of students and faculty who are working on this project, and PNNL team is led by Kendall. Oh, okay, very nice to meet you. And Monish, I saw Monish again this morning. So, and this project is in close collaboration with utilities. Mike Didish from Avista is our utility partner, and also we are working with Snohomish PUD, and with the regional tribes, and I know time is short, so I will try to go through all the technical descriptions. You know, it just are not, I don't think I can match your speed, but I will try what I can. So the first part, you know, Kelly and Larry talked about this public safety power shutoff. How can we do this in a more scientific way? So we are developing some methods to come up with some metrics for risk assessment. Because in our opinion, you know, tripping a transmission line or shutting it down will have consequences. It will overload the neighboring lines, and also depending on the distribution, the effect on the, or the impact on the customers will be different. This depends on how much dispatch crews you have to bring it back on. And so we are developing some kind of a model to study these impacts in depth. So that is part that my colleague Rafika is leading. And this is also related to her NSF project, and maybe there will be posters in the afternoon that you can learn more about. And the second part is once there is say there is an overload of a transmission line, then what are some of the best mitigation strategies? If we have to trip a transmission line, can it be possibly avoided by bus splitting or maybe redispatch or using storage? And this quickly becomes a very high dimensional combinatorial problem. So how can we maybe use AI for speeding up? And this is what Yash is working on, and so you can talk to him in more detail. And then the other part is typically in a resilience situation, we are in a system configuration that may not have been studied before. So we may have several microgrids. So how can we ensure system stability, frequency compliance, and in terms of meeting the customer needs? So that becomes a problem in dynamic modeling and in stability analysis, and Wade talked about this. Those systems may be dominated by inverter-based controls. So how can we use some of those to better manage the system in those conditions? So that is another aspect of this research. And one of the important components of this research project is pilot studies. And in our case, we are working with the Spokane tribes, with Avista, and also with the Chulalup in the Seattle region with Snohomish PUD. Both tribes have received some state funding to commission microgrids already as part of the clean energy funds. And the utilities, Avista and Snowpad, are working closely with them, and we will help them maybe develop a roadmap for the future and to do studies to make sure that the microgrids are as planned. And again, this question that came up in the morning, how do we do some kind of an economic justification? If it is just for those rare events, then that will be difficult to justify for operating the system 24/7. So how can we maybe combine that with some utility benefits that would provide savings over time, and that can justify such investments in the future? So that's the WSU part in a quick run through. And PNNL part, I'm going to be even faster. So, we have several tasks that I am not really very familiar with, so I would encourage you to talk to Kendall and Monish for the details. They are developing metrics, they are developing models, and again the economics part, and also some restoration strategies. So there is a lot going on in this project. And another important component of this effort is the workforce development that Monica brought up this morning. So this is an important aspect of our project, especially since we have these 12, 13 universities which are working together with also the Northwest Indian College. So we have plans for several workforce development activities. PNNL is very much part of those activities. So I will stop there and again give back some time. Thank you.
Thank you very much, Mani. So our next speaker is Brad Ross from PNNL. He has done a lot of work on power electronics modeling, power system transients, and in recent years he led a lot of efforts on large load modeling. So he will share some of his work for large load modeling. So Brad, you are very lucky. The previous two speakers saved a lot of time for you.
Yeah, it's like when you're at the, they pay for the next coffee in line. I'm not paying for it. I'll probably use all my time. Let's see. This is on? Great. Okay. Lovely. So is there anyone here who has not heard there's a ton of data centers springing up everywhere, load demand is skyrocketing? It's probably right. We've all very familiar, right? So I'll skip a little bit of that. Instead, I'm going to dive right into some challenges and opportunities pertaining to power electronics technology, where some of those technologies are being viewed as solutions for a lot of the technical challenges that we have in front of us. Okay, so right, we've got a bit of a mixed audience. Some of you I recognize are extremely knowledgeable on all the nitty-gritty, and then some of y'all work more at a higher level. I'm going to try to talk to everyone simultaneously, which maybe is a bit ambitious on my part, but I'm going to try and highlight some of the major themes as well as some of the key technical nuances that are going to help those of you who've been doing power electronics for a long time recognize how your existing work and expertise plugs into these new challenges. So up here I've got simplified schematic of a lot of these large digital loads, or cryptocurrency mining, traditional data centers for cloud computing, AI data centers are primarily designed for training large language models. Generally, the load mix comes on one of three kinds. You've got, I'm going to call the lower criticality computational processes, for instance, crypto mining, where it really is thousands and thousands of switch mode power supplies connected up at a single site. Data centers generally have a very sophisticated, highly redundant power system, primarily uses double conversion power, uninterruptible power supplies. However, there's a strong push with a lot of the vertically integrated data centers to move to a more distributed in-rack battery backup, which is totally different power electronics design than the more traditional UPS. If you want some more details, I highly recommend the NERC questionnaire for collecting info on data centers. It kind of gives you a feel for the different technologies, the things that, from the grid perspective, people are trying to understand. I'm going to focus on three different kinds of challenges that are on three different time scales and talk about some power electronics applications. The first one, short interconnection timelines, right? So, one of the things that stands out about this topic is how quickly it's moved. And it's not surprising considering, the power industry, which would be considered, not as nimble as other industries in certain circumstances, with the tech industry, which is known for being, very fast moving, and always at the forefront, always pushing the limits. And so this is coming together, where to stay competitive, these data centers want to connect within 2 years. But securing transmission line rights of ways, the things you need to serve gigawatt scale loads, can take 5 to 10 years. I think that this, this was originally from ERCOT. I don't think you can get turbines this quickly anymore since I first put this together, so those might be sold out. So that's the first issue, right? So traditionally, there have been cases where sometimes power electronics are used to solve certain contingencies, certain problems until you can build those transmission lines. Those kind of use cases are growing very rapidly in their occurrence. The second issue, which you might have heard, there's been a lot of event analysis around, is fault risers. So one of the reasons why data centers have uninterruptible power supplies, those are not cheap pieces of equipment at that scale, is to provide the highest quality, the most stable power for their processes. So their websites, the services they provide are competitive in the market and provide that cutting edge performance. And for that reason, whenever there's a disturbance in the grid, to protect their process, they come offline. And they've been doing this for a long time, and it hasn't really been a big deal, but all of a sudden, very rapidly this has grown to something you can see across an entire interconnection, right? And so this has raised the question of, how do we deal with these very, very fast, rapid changes in energy demand that can follow whenever a fault or disturbance occurs. The last kind of challenge, which I will refrain from getting too into the details of, are oscillatory demand profiles. So the way I understand it, I'm not an AI expert at all, is that the best way to train very large AI models is to control all of the individual compute units in exact synchronism. So, really you're putting a job on 200,000 GPUs at the same time, and then they finish their job and they have to transmit that data, and the demand goes away. As luck would have it, the frequency of many of these profiles tends to overlap with frequencies that propagate really well throughout certain areas of the power system, throughout very expensive and critical pieces of equipment such as steam turbines, and so that's caused a lot of concern, right? And rightly so. The bottom plot is a frequency variation that was taken from a large natural gas turbine. Part of the reason why the y-axis has been redacted is because it's proprietary and involves a generator that was actually permanently damaged, greater than 25 megawatts as a result of them trying to operate with this oscillatory load profile. So a lot of concerns around this. The common thread that's probably emerging here, right, is we have very, very rapid changes in energy demand. It might be for the next 5 years, the next 5 hours, or the next 5 seconds. And so you see on all these time scales, right, very quick changes in energy demand, and that rapid control and rapid response is one of the ways in which power electronics bring a lot of strengths to the table. For the 3 challenges I talked over, I'm going to talk a bit about the ways people are looking at solving these problems or managing them with power electronics. So for the shorter interconnection timelines, I mentioned briefly how if you have certain contingencies or certain scenarios where you don't want to allow this much load to connect until you build more capacity, you can use energy storage to alleviate those contingencies. I think the most straightforward example, right, is the power system has enough capacity to serve this load 99% of the time. That last 1% can come from energy storage that's located close to that site. And then, I guess I'll touch in a little bit briefly on that. This could also be an application for some demand, demand response and things have been things we've traditionally looked at for dealing with these kinds of situations. What I know so far is that the cost incentives for those data center providers, the cost of electricity is not a major portion of their business model. So just kind of bear that in mind when you're looking at these kinds of scenarios. But there are more sophisticated options or more sophisticated scenarios involving voltage stability, angular stability limits, things like that, where the same basic philosophy applies. For the fast load tripping, this is still unfolding a lot in that people are trying to figure out what can be done with the power electronics that are already at these sites, right? You may have noticed that an uninterruptible power supply by design has battery storage in it, right? So how much can we leverage that? But of course nothing comes for free, right? You have a piece of equipment that's specifically designed to support the load no matter what. And if you're going to ask it to start supporting the grid too, it may no longer actually provide the performance that the load, they bought it for. You only have so many resources. So energy storage is another solution to that. So you have power electronics interface. Even if you lose a large amount of energy, as long as you have enough, fast frequency response capability with your energy storage and your power electronics, then you can mitigate these effects. For the third one, the oscillatory load profiles, you can see kind of, right, a similar trend, right? The single statement is, well, it can get you the energy you need very quickly, right? And so for the oscillatory load profiles, locating power electronics closer to those sites, there's a couple different control methods, definitely glossing over some details, but that people are looking at to smooth out these load profiles and give something a little bit smoother to the grid so you don't have to worry as much about the oscillation propagation. So I'll talk a bit briefly about some of the, right, because a lot of people are talking about this topic, there's a lot of ideas floating around. I'll talk about some of the main things. So right, there's a lot of different energy storage technologies out there. I'm also not that much of an expert in energy storage, but most of these can be connected to the grid through a power electronics interface, and that's what gives you the speed that you need. I will say that these applications, for those of you who are familiar with fax devices, static bar compensators, those traditional technologies really, the studies I've seen so far have shown that those are not necessarily going to be sufficient. So for example, yes, you can use an SVC to raise the voltage during the fault, but there's no way that you're going to be able to add enough dynamic bar support to keep those loads from tripping off. It's just, they're just too sensitive. It's not, it's not as simple as adding an existing device. I also want to note that there's kind of like two categories of, the long duration and the short duration storage technologies that people are looking at. So an eStatCom is a StatCom device, so power electronics kind of system support device, but now they're integrating it with supercapacitor technology that gives you on the order of tens of seconds. So you might be able to tackle the latter two problems to some degree, but it's not going to last for 4 hours. The hydrogen fuel cells, of course, lithium-ion batteries, right, are being talked about for the oscillations. However, there's also a use case for more high life cycle battery technologies because, right, if you're oscillating a load, you either have to make the battery significantly larger than the load, or else you're going to wear it out in a year. And that's why you can't just use the UPS batteries to smooth out every load profile. I'll also say that there's, we can be clever about the sizing, but there's ultimately no escaping the conservation of energy. If you have a 100 megawatt load fluctuation, that 100 megawatts has to come from somewhere. There's no very clever way to control a 10 megawatt battery to deal with that. And so there's a lot of thought that this is going to have to be a yes and type solution where maybe there's an improved GPU level control that gives us some amount of attenuation, and then you get the rest of that with your batteries or supercapacitors or what have you. So it's not necessarily looking like, oh, we'll just slap this thing on and it'll go away. I also want to talk briefly, someone brought up DC power systems earlier. All right, I love DC power systems. I wish we had more of them, but I understand why we don't. But interestingly enough, there's all these stages of power conversion going on. And I think for a long time, people recognize, oh, power electronics rich environments, let's go to DC distribution, pull out all those extra converters, save money, save space. This is beginning to gain some more significant traction with the vertically integrated data center designers, where we're starting to see they're designing their next generation of data centers operate at 600 volts DC, 1 kV DC. They're building up a power electronics supply chain to actually provide those kind of power levels, which it's economics, right? If there's if they want it badly enough, they will build it. But historically, there hasn't necessarily been that enough demand to drive those products into the market. But now we're seeing that happen. And that's it. Yeah, thank you very much for your time and attention.
Okay, thanks all panelists. Sorry, we're open for questions to our last panelist. Okay, one-on-one questions. No, okay, all right. We're open for questions to our panelists.
I can yell. It's okay. Jacob. I have a question on the Grid Cred program for Jacob. Jacob,
Yes.
are you getting like a regional platform like you're looking at needs the engagement level from the region? I know that's been a challenge. Are you starting to make some progress on that, and how's that going?
Yes, yeah, good progress this summer, good engagement, many members of the AGI, as well as other participants in this room. But I think the thing too that's going to help there is, having the collaborative problem to solve. And so I know that there's actually a kickoff meeting for a multi-regional entity problem to solve using the platform, scheduled up for the very end of next month. That's the next piece that we have to kind of get to is practical use cases. So we can talk through examples at the poster session, but I would also really appreciate any industry participants to go ahead and approach and let's talk through what has been something that has required some work with your neighbors to try and get traction on. Thanks.
The questions?
Hello everybody. I'm Yash from WSU. My questions to Engineer Ross. So you mentioned two graphs. They were discussing about the frequency that these data centers operate on, or the frequency they push towards, or the load frequency they reflect on the power system side. Can you please elaborate on that? Why I'm asking this is because I work in AI and I try to make these decisions. Those are combinatorial decisions based on AI. And even though the methods that we try to develop do not really make use of such high computation power when it comes to application, but when it comes to training, we do use these Monte Carlo simulations, and these servers and data center would help in long run if we have to generalize these things on grid level in the future, of course. So if we are reliant on running our power grids on data centers, and data centers themselves are proven to be such great threat to power grid, I think it turns out as a loop.
Yeah, that's a great point. So I'll share an anecdote that a principal engineer at Microsoft shared. So he'd been working on large language models and the power systems for them for probably 30 years. And he said, well, we first started doing this, and it broke all of our power supplies. But then we got past that, and so we made it bigger, and then we started doing it, and then it broke all of the controls at the site. And so we fixed that, and now we started doing it bigger, and now the grid has finally noticed that we've been doing this for 30 years. And so, right, it is definitely reaching a new scale. I think that, what I mentioned before, right, there's a lot of really smart people on the AI side working on this problem too. There's, NVIDIA has like features they're trying to develop for their GPUs to maybe minimize these swings, which include just burning power on the low parts, which I guess that's one way to get rid of an oscillation, just stay at the peak all the time, eat space. But I think I don't want to overstate that it's like a huge threat to power grids. Right? It's just a characteristic of a load that we'll figure out how to solve. We have technologies. They're not easy, right? There's still a lot of work to be done. But my takeaway when I saw this, I'm like, oh, this isn't possible.
Hi, this is Veera Benacota, California, independent consultant. One of the things that I notice is that where all the power-related members are trying to cope with the load in addition to the already existing renewables related issues, etc., with the data center loads. My question is there any national level entity that is really checking if the solution, the AI-related solutions that are being posed, is that the right solution? That so much of load is being consumed. So it's a bit surprise to me, suddenly, to me as being as a player for a long time in this. So I just want to ask to summarize, is there any federal entity that is evaluating that the AI-related solution for the nation, is that the right solution?
I would refer the question to Mark.
Mark, is there some sort of reliability that can be
I was just trying to hide over here. yeah, we're working it. We've got one report that's been put out that identifies what are some of the risks to the bulk power system. Another report now is going through a comment from industry that identifies the gaps in guidelines and in standards and who's responsible for those gaps, right? Because the way in which NERC writes standards is we bring industry together to write them, right? So who's responsible? Is it going to be the large load owner or an operator? Or is it something where it's go to the LSC and say, you're tagged, you're it, so that we can manage the performance of the system. And you know, we've seen some of these line to ground faults that no right through. We've seen some of the AI, you know, excitation. You might see load levels that can kind of excite small signal stability. So we're also issuing an alert, probably the first week of September, to industry saying, hey, you know, do these things when you start interconnecting. Look for these things, demand these things from those that you're integrating, and also trying to get an idea of how big the risk is, who they're talking to. They won't tell us, of course, but how big, what kind of scenarios are they looking at. So ultimately, this is going to end up being with the standards. Now, the standards here are written by industry to follow those, and that's performance based. So we're not going to tell people how to solve it. For example, if you look at what happened in Dominion, it was 3 strikes and you're out with a line to ground fault, I think, and of course after 2 strikes the load went away. So then then I know that Dominion's working with those large loads and say, well, how do we solve this problem so that you don't go away when I need you to stick around, and vice versa. Of course, they don't want to go away; they'd rather keep running. Yeah, I think they're solving those kind of problems. But we want to make sure that we do it on an interconnection-wide basis, because what happens if Dominion impacts others, and if others are not doing this, then they're going to be having loads coming off. And so we want to be able to work consistent. So it's negative generation, right? So it's the opposite problems, but we're working hard to kind of fix those things quickly.
Sorry.
No, that's, of course, there's 2 bits, right now. That's operational reliability. Now, do we have enough energy? Well, that's up to the states to build the plants. I can't do that.
Sir, a follow-up, probably misunderstood. Maybe it's none of our business to see whether the load that is coming onto the grid is right, just to address it because it's coming. I don't mean, I have no doubts about the poor folks addressing that. My question is that because at national level, in a different perspective, that whether the solution provided by the computer scientists for these AI-related things, is that the right solution that the data centers coming all over and heavy loads are coming? That's my question. It is not really the power grid related, but it is a AI folks, whatever solution that is providing the AI, which is consuming heavy loads like this, is that the right solution for the nation? Maybe this forum may not be. Is there any agency which is overlooking that?
That's a policy level question. I just wanted to add to Mark's comment, and this may be news to you, Mark. You know, NASP, which is the North American Synchrophaser Initiative, which is it's an organization that includes many of the utilities, and it's about monitoring the system in real time to help the operators get some situational awareness. And one of the recent task forces that has been formed, it's a task force to develop NERC standard authorization request to mandate or to develop some requirement on monitoring of these operations he talked about. Currently, the capability in different utilities is very different. Some utilities have active systems that they use, some don't, because there is no requirement to monitor them. But there may be some oscillations or some events going on because of the loads that maybe the utility is not even aware of. And so this is an effort that we have started to develop a SOAR request in NERD to kind of formalize that monitoring technology.
Yeah, makes sense.
Right, one last question. Okay, we answered all questions. That's great. So let's thank our panelists once again. Thank you so much
Thank you. So if you have any questions to the panelists and our previous speakers, please feel free to ask during the break session. So our